want to learn about the properties of definite integrals, don't you? Yeah, sure we do. So I have a couple questions for you here, like kind of like you just to go through, try to answer them the best you can. And then there's an actual definite integral, and I'd like you to find it without the calculator. If you want to check your answer when you're done, that's fine, but try to use the fundamental theorem of calculus, the FTC, as we call it in the biz, to evaluate that. All right, I'll check the homework. How was the homework? There were some tough ones? 2 tiers, mixed reviews. Okay. All right, I'm checking homework. Okay, who can tell me, when you're looking at an antiderivative, how do you tell if it's a definite integral versus an indefinite integral? Yes, gentlemen. Wow. It's got an upper and a lower limit of integration. It's got little numbers. Little numbers. So if you want to say it as little numbers, fine, as long as you understand. But we call those little numbers limits of integration. All right, next question. Do you need the arbitrary constant, the plus c, if it's a definite integral? Nope, you've had your turn. Sorry, Manny? No, because they cancel out. Not only did she give me the no, she gave me a reason. I just gave a no, but I like the reason. Oh, yeah, because they'll just subtract out, so you don't need them. Now, suppose you had to list the basic steps to evaluate a definite integral, and I'll just call it the definite integral from a to b of f of x. I'm just going to move that guy. Nope, because it's still a marker. Oh, all right, wait. Order of operations. Maybe first. Okay. If you want to evaluate a definite integral of a function, let's tell me the first step. Jessica, find the antiderivatives. Step 1. And we would call that antiderivative capital F of x. I can put that there. So capital F of x. You always use the same letter, but the upper case. Okay, so you found the antiderivative. Are you stretching, John? Is that you're raising your hand? I will take that. What do you do next? Plug in the upper limit of integration. So that'll give you capital F of b, right? All right, Manny, I'll let you go again. Nice. Plug in the lower limit to find capital F of a, the antiderivative at a, and Gina's going to finish it off. Subtract the lower limit from the upper limit, so it'll be f of b minus f of a. Nice. That's not so bad. You guys seem pretty good at that. Now, whereas an indefinite integral results in a function or relation, a definite integral results in a, I have to go, Cameron? A number. A number. Definite integrals give us numbers. We love the numbers. And then finally, no more words. I want you to actually find that number. Evaluate this definite integral. All right, who's going to tell me the antiderivatives? My step 1. Gina. Correct. Correct. Nice. And then we draw the little line, evaluated from 1 to 2. How are we doing? We're doing great. All right, so I like to set it to 2 sets of parentheses so I don't forget to distribute. It's up to you. All right, who's going in there first, the 1 or the 2? 2. All right. Oh, that's correct. On the calculator, you do the lower first, but by hand, with the fundamental theorem of calculus, the upper first. What's 2 cubed? 8/3 plus. What's 3/2 of 2 squared? Nice. Minus 2. Okay, so we plug the 2 into the antiderivative. Now we got to plug the 1 in. 1 cubed over 3. 1/3. Oh, this one's easier, huh? Plus 3/2 minus 1. Now, let's pretend we're not dependent upon a calculator. Let's get back to arithmetic, shall we? Okay, let's combine like terms. So first of all, I see we have some thirds here. How many thirds do we have all together? 7 thirds. Okay, I like that. We have some integers. We've got a 6 minus 2 and then minus a negative 1. So 5, right? Because you'd have 4 minus negative 1. And then you got that over there, so what's the last term going to be? Nice, you caught the minus 3. Right, being subtracted. Well, with fractions, we need a common denominator if we want to add or subtract them. 6 would be beautiful. I'm going to rewrite each of these fractions with a denominator of 6. So 7 thirds is how many 6? Yeah, 14 over 6, right? If you multiply the denominator by 2, you multiply the numerator by 2. 5 is how many 6? 30. 9. So how many 6 do we have? $35, 6? I like it. So there's a number just shy of 6, right? 36, 6 to be 6 is a little less than that. Nice. Let's see this homework. Let's see what's going on. Yes. I think all the asterisks, that's supposed to be negative signs, and then there's a P in one of them, that's supposed to be a pi. Sometimes with these programs, it doesn't, like, understand what to do. I wonder how many of those Gov kids actually did their homework. None of them. Should run down there and check their homework. Awesome. Gov kids, we're coming for you. So we'll go over whatever ones you want to go over. Yes, Cameron. 5. You're going to start out with number 5. What are you going to say? Okay. Think about the ones you want. I know 5 and 14 for sure. Is anyone still checking their work? Checking the answers, I mean? You're still checking? 16? Okay. I can move on. Pages in. Okay, so I'll start off with number 5. And I actually am really glad you asked this one. We have to take the antiderivative of 1 plus x over rad x from 1 to 4 x. Now it's not u sub here, but what do we have to do? You can move it up or just divide each term separately. Either you multiply every term of the numerator by x to the negative a half, or you divide each term by x to the positive a half. I have to say, when I was looking at those tests, and you guys did great, by the way, but there was a lot of problems. I think it's easier just to break it up and keep it division. In other words, just put each term over x to the half and then simplify each term. I'll just do this first, but then I want to talk about what I saw. So if you just take each term of the numerator and put it over the denominator, you can break it up like this. But then you got to simplify. Now, if you keep a division, as I did, if you have the same base, you subtract exponents. Now, the first term is 1 over x to the half. How would we rewrite that? X to the negative 1/2, right? All we're doing is bringing it up. Now, the second term, it's an x to the first over x to the half. So what do you get? Well, you subtract, but it's the exponent on top minus the exponent in the denominator, so it's to the positive 1/2. So that's what you have to do first. Then we'll integrate each term. But what I saw people doing, and you could just ignore this if you want to, people don't like to divide the whole subtraction thing. I guess it's negative or something. I don't know. It's all right if you want to rewrite it as 1 plus x times x to the negative 1/2. But what I saw a lot of people doing, instead of multiplying by x to the negative 1/2, they just added x to the negative 1/2, which didn't make any sense. You have to distribute the x to the negative 1/2 now. All right, so if you distribute the x to the negative 1/2, because you're multiplying by x to the negative 1/2, you have x to the negative 1/2 times 1. That's x to the negative 1/2. Now, if you're multiplying, you add exponents. So x to the first times x to the negative 1/2, it's still x, it's x to the 1/2, okay? It's just you either divide each term by x to the 1/2, or you multiply each term by x to the negative 1/2, okay? So to get to that point, now we can just go ahead and get the antiderivative of each term separately. We use power rule, right? What's the antiderivative of x to the negative 1/2? Oh, that was nice. I'm going to just, all right, can I do the 2 radical x? Because it's 2x to the 1/2, yeah? Nice. Okay. Now, let's use the power rule in x to the 1/2. It's 2/3. Now, it's x to the 3/2. X to the 3/2 power over root. Because it's 2/3 x to the 3/2, right? So that's the antiderivative. We want to evaluate it from 1 to 4. All right, let's plug 4 into the first term. What do we get? 2 times red 4 is 4. Plus 2/3 times, what is 4 to the 3/2? So the square root of 4 cubed. 8. So that's times 8. Now we plug the 1 in. 2 rad 1. 2, right? And then plus 2/3 times the square root of 1 cubed. Oh, that was not real. All right, so we've got 4 plus 16/3. I'll distribute the negative, what the heck. Minus 2 minus 2/3. So altogether we have 14/3. And what's the constant? Plus 2. Common denominator, 3. So the numerator, 2 over 1, is how many thirds? 6. Final answer, 20/3. Oh no, that's not there. Mixed numbers. How do you go from an improper fraction to a mixed number? Oops, know it? And then what do you do? Okay. Beautiful. So you divide 3 into 20, and you get 6. Right? The remainder would be 2. So 2 over 6 and 2/3. Okay, so that was 5. That took a little bit, but well worth it, right? Any questions? Anyone need me to scroll up or down? Okay, the next one I heard, I think, was 14. 14 is scary. did 14? Yeah, right? Okay. It says if the definite integral from 0 to 9 of f of x dx equals 12, they want us to find the antiderivative from negative 3 to 0 of x f of x squared dx. Whoa. Anybody have any clue what we're going to do? Like, even if you didn't have it up there, if you wanted to integrate this, what would you have to use? Power rule? Well, it's f of x squared. X squared is being plugged into a function. So that's the inside. How do you take the antiderivative of a composition of functions, which is what this is? U substitution. Tell me what u is going to equal in this case. X squared. So what does du equal? 2x dx. So what do I need inside? A 2. I'll put it here. So on the outside, 1/2. Let's rewrite this, and let's also convert over the limits of integration, like everything's going to u's and d's in terms of u. So we've got a 1/2 on the outside. We'll save the limits of integration to the end. Now, we've got 2x times f of x squared times dx. How could I rewrite that? F of u times du, right? We've got the f of u. And the rest of it, the 2x dx, that's just du. Now let's get the limits of integration converted. U is always equal to x squared. So the lower limit of integration was negative 3. That's x. What would u be if x was negative 3? 9. The upper limit of integration was 0. What would that make u? U equals 0 squared? 0. To whatever u is, the definition of u to convert the limits also. Oh. Okay. This one, it's too bad it's in the opposite order. That was going to come up today. All right, well, see, the thing is, you'll see this today, if you switch the limits of integration, think about when you find a definite integral. You get the antiderivative, you plug in upper, lower, and you subtract, right? What would happen if instead of plugging in the 9 first, like if you plug in the 9 first, then the 0 and subtract, you get 12. What do you think this is going to equal if you subtract in the opposite order? Wow, you guys are good. I didn't even give you the property. So this would be negative 12. Well, when you find a definite integral, first thing you do is you get the antiderivative, right? Then you plug in the upper and then the lower and you subtract. Well, the only difference between this one, the one they gave you, and that one, other than the variable, it doesn't matter what you call it, is the limits of integration are switched. So you plug in, it's when you're going to be subtracting in the opposite order. In this one, you plug in the 9 to the antiderivative, and then the 0, and you subtract in that order. And then if you get 12, if you were to subtract in the opposite order, which you would do here, you get negative 12. 5 minus 2 is 3. 3 minus 5. What did I just say? 5 minus 2 is 3. 2 minus 5 would be negative 3. When you change the order that you subtract, you get the opposite answer. All right, so that was tricky. To do another one? I don't know. No. Let's just get it for it. So, all right, yeah, let's do this. Do this. Oh, I put a bunch of spaces in. Okay, so today I want to talk about properties of the definite integral. And some of them you already know, because we had them for indefinite integrals. Like this first one. What can you do with a constant multiplier? You just pull it out front. You can still do that if you have a definite integral. So if you have to evaluate a definite integral, go ahead, like here, you can pull out the 4. And then just evaluate the definite integral when you get your answer multiplied by 4. I won't go through the whole thing, but we all comfortable with that property? Yeah, we know we can do that. Oh, same thing. Second property of a definite integral we've also seen before. In fact, make this a plus or a minus, because it doesn't matter whether it's addition or subtraction. If you have to take an antiderivative of either a sum or a difference, what are you allowed to do? Do them separately. And that's what you can do with definite integrals. So what you're allowed to do is take the definite integral of f of x with respect to x from a to b, and then add or subtract the definite integral to b of g of x. Now, I'm not saying you're ever going to want to do that, but you can. It's a property. You're allowed to do it. Only with addition and subtraction. Don't even think about it with multiplication or division. So like with this one, if you wanted to, I think it would be more time consuming, but you could take the antiderivative of 2x from 0 to pi and add the definite integral from 0 to pi of cosine of x. You know when this helps you? Like on the AP exam, sometimes they'll tell you the definite integral of one of them. They'll say the definite integral, and I'll just call this of f of x, like this part is 3. But you still have to figure out the definite integral of the other part and then add the two answers together. Yeah. Yeah, it's like you have to find the antiderivative of the term that didn't. So. Yeah, I think that there's one like that on the homework tonight. Yeah, that's good. Tonight? All right, so you're probably like, yeah, we know these properties, no big deal. Show us something exciting. Look at this problem. Is that exciting enough for you? How'd you have to do, like, having to do that? The definite integral, look at this one, from pi to pi of cosine. Oh, no. Well, integrating that, I couldn't do it. Well, I don't think I could. No, I don't think there's a technique for that one. Oh, no. What are you thinking, Ellie? Yeah. All that for just 0. Why would this be 0? Yeah, that's true. You can think of it two ways. Either think of it as being, okay, you got this function f of x, and you're taking the area underneath it from a to a. Oh, no area. Okay. And the other way of thinking of it, like Ryan was saying here, if you got the antiderivative, right, call it capital F, and you had to evaluate it from a to a, you'd be subtracting the same thing. Capital F of a minus capital F of a. Yeah, well, that's what this property is saying, is that whenever the lower and upper limit of integration are the same number, it'll be 0. I don't think this one has a name. I'm not sure. I don't think so. So I always get people in a test. I'll warn them, these are the properties. I'll put something like this on, and people will start telling me, like, cotan over secant squared. Plugging in stuff. No, you gotta look. You gotta look. You've been warned. Silly kids. What do they know? All right, so this is the property that kind of came up with that one question we went over. And I just want to make sure you understand why you would get the opposite value. Okay, so let's say we wanted to evaluate, I'm going to work on this side for a second. If you get the definite integral from a to b of lowercase f of x, first thing you do is you get the antiderivative. What would we call that? Capital F of x, right? And we evaluate it from a to b. And what would we get when we do that? Capital F of, which one first? B minus capital F of x, right? Now on the other side, forget about that negative for a second. I'll show you why that has to be there. Let's just say we wanted to get the definite integral from a to a. First thing you would do, get the antiderivative, same antiderivative, capital F of x. Well, what would you plug in first? Yeah, right? So you would get capital F of A minus F of B. Yeah. If you take any two numbers, let's say 9 minus 1, that's positive 8. 1 minus 9, negative 8. Whenever you subtract in the opposite order, you can get the opposite answer. So these will always be opposites. So that's why this negative has to be here. I'll put that in here. Or else they won't be equal. So if you put the negative in, just save it for the end. Now if you distribute the negative, you have negative f of a plus f of b. Positive guy goes up front. So the moral of this little story is, if you know the value of a definite integral, whenever you switch the limits of integration, you can have the opposite value. For example, suppose you know the definite integral of f of x from 2 to 5 equals negative 4. What would be the value of the definite integral from 5 to 2? Positive 4. Right? So when you switch limits, that's fine. You're just going to get the opposite value because you've subtracted in the opposite order. Make sense? Got it? So that's a property. Here comes a great property. You can have fun with this property. How many of you have ever heard of the whole is equal to the sum of its parts? The sum of parts equals the whole? Okay. Guess I would be kind of the same. Okay. All right, well, that's what I think of this as. Like, if you think of the definite integral of f of x from a to b, now if f of x is positive, we've got all this area under the curve from a to b, right? It says that's equal to the definite integral of the function from a to c. Okay, now think about it. That would be this area here, plus the definite integral from c to b. All right. So what you're allowed to do is you can always break up a definite integral anywhere you want. And c doesn't even have to be between a and b. You could break it up anywhere you want. Now you might think, so? I'm not going to do that. I'm going to ignore this part of the lesson. All right, well, if you look on your homework, look at number 16 for a minute. Look at number 16. Yeah. See? Oh, no. I don't even remember what it was. I have to look. You have a piecewise function. So y is equal to 3x squared when x is negative, less than or equal to 0, and equals negative 1 when x is greater than 0. And they want you to evaluate a definite integral from negative 1 to 5. What do we just like pick the 3x squared or the negative 1 randomly and just put in for f of x? What is it? See, like we can't say yes. Okay. But I can't just have one definite integral. I got to break it up. Where would I want to break up this definite integral? At what value? At 0, right? If you want to get the definite integral from negative 1 to 5, you would find the equals. You would want to find the definite integral from negative 1 to 0, because that's where the piecewise function splits, plus the definite integral from 0 to 5, right? Negative 1 to 0. The next one would have to be from 0 to 5 if you want to get the whole thing. I lost you? Okay. Yeah, then you can plug those things in. Here's the thing. With a piecewise function, f of x is not always the same thing. It's not like I could just put in the 3x squared or the negative 1, because it depends on the value of x. But if you break this up, the definite integral from -1 to 5, I can break it up at 0, because that's where my piecewise function split is at 0. See, now I know what I can put in for f of x if the x's are going from -1 to 0. What does f of x equal for x's between -1 and 0? I read it that way too the other period. But from -1 to 0, x is negative, right? So for f of x, you can put in the 3x squared. For x's between 0 and 5, what does f of x equal? -1. See, then we can just do them separately, and we'll be able to do it. So this is, then you'll have to take the antiderivative, plug in the upper and lower, and subtract. You have two definite integrals. But you see, it's helpful, especially when you're trying to find the antiderivative, a definite integral of a piecewise function. So, now let me finish that up. Okay, where was I? Okay, so that's one of the properties. You're allowed to do it, and again, C does not have to be between A and B. It can be any number you want. You can break it up. And this will give us a chance to play a little game that I call the number line technique. I think you're going to like this. So let's say you're given the values of different definite integrals, like from 0 to 1, it's 6, from 0 to 2, it's 4, from 2 to 5, it's 1, and then they ask you to find some other definite integral. You're going to use something called the number line technique. You draw a number line, and you mark it off at all limits of integration. So tell me what numbers I should mark it off at. What are my limits of integration? Look at all of them there. What do we got? 1, 0, 2, and 5. So 0, 1, 2, and 5. And the second thing you got to do is fill in the given values, but it has to be true that the lower limit A has to be less than the upper limit, or else you got to switch them. Okay, so the first one we're given, they tell us the definite integral from 0 to 1 of this function is 6. So this one's good. 0 is less than 1, so I can use the 6. So what I do on my number line, I just mark off from 0 to 1, I've got 6. The one next to it says the definite integral of this function from 0 to 2 is 4. Again, I just make sure that the 0, the lower limit's less than the upper. It is, so I can use the 4. So from 0 to 2, that's 4. Now before I go on to the next given, if I know from 0 to 2 it's 4, and from 0 to 1 is 6, what would from 1 to 2 have to be? -2, right? Because the 6 plus -2 would be 4. Okay, that's good. All right, so take care of those. Next given definite integral from 2 to 5, it's 1. And again, 2 is less than 5, so I can use the 1. If it wasn't, I'd have to switch it and use -1, but this is good. 2 to 5, it's 1. Oh, ran out of different colors. All right, so from 2 to 5, I've got 1. Everything with the number line technique looks left to right. So what they're asking us for the definite integral from 5 to 1. Before I answer that, what would the definite integral from 1 to 5 be? So from 1 to 5, it'd be -1 because it's -2 plus 1. That's -1. So they want us to say what the definite integral from 5 to 1 is going to be. It'll be +1. Ta-da! The number line game. Oh, technique. Isn't that fun? I have a second one. I don't know if we can do it fast enough. I have an example B is just a little extra practice with that one. I like it. I wanted you to try, there's one of these that we'd have to switch We can't use it as is. Do you see it? Which one can we not use the number that they gave us? Yeah. So you would have to use from 2 to 5, that's -4. So you can only put the numbers down if you know the lower limit. Oh. Oh. So, I wonder if I could. I don't know. It's getting tight here at the time. Oh, great. I got the phone ringing. Okay. I'm going to mark this guy off. What numbers are we marking this one off at? Got a -3. Oh, no one got an answer, right? It was too quick. You'll never know. It was. It was very good. It was. All right. Well, never know. We'll do that last example tomorrow.